These are your notes for Unit 4, Day 7 of Calculus. If you would like to see your warm-up, the review question, or any homework questions we covered in class today, just look at your finished notes. So today we're going to talk about a couple more theorems. We're going to talk about the mean value theorem and Rolle's theorem for derivatives. We're going to talk about the mean value theorem for integrals, and we'll talk about how to find the average value of a function, and we'll review how to find the average rate of change of a function. So let's start by reviewing displacement, velocity, and acceleration as derivatives, and then we'll introduce how to view them as antiderivatives. So displacement we'll use as x of t, so that's our displacement function. And remember, this is distance. This is different from distance because displacement can be negative. And if displacement is negative, you view it like a vector, and that negative indicates direction. So if you have a displacement of -3, then that means that you have a displacement of 3 to the left or in the negative direction of where you started from. If you take the derivative of displacement, you get your velocity function. And so that is your instantaneous rate of change. So the instantaneous rate of change of displacement is the velocity. If you take the second derivative of displacement, or if you take the first derivative of velocity, you get your acceleration function. And that is the instantaneous rate of change of velocity. And so we could call this meters for units for displacement. We could call the velocity meters per second, and then the units for acceleration would be meters per second, or meters per second squared. Well, if you want to go from acceleration back to velocity, you do the inverse operation. So if you integrate acceleration, you get back to the velocity function plus some constant. So if you want to undo acceleration to get back to velocity, you integrate. If you integrate velocity, you get back to your displacement function plus some constant. And so that is the relationship between displacement, velocity, and acceleration as both derivatives and antiderivatives. All right. So if velocity is instantaneous rate of change, how do you find your average rate of change? So an average rate of change is found by finding the original function at b minus the original function at a over b minus a. So if you want to find the average rate of change of f of x on some interval a to b, then it's like the slope formula, the change in y over the change in x's. So it's f at b minus f at a over b minus a. So this is very similar to the slope formula, except for it's in function notation. So suppose that a particle moves along a coordinate line so that its velocity is given by 2 plus cosine t. Find the average velocity of the particle during that time. Well, average velocity, you want the units for velocity, so you want meters per second, or you want the change in displacement over the change in time, because that would give us the meters per second for our units. Well, if they gave us a velocity function and we want the average velocity function, we need displacement. So how do you go from velocity to displacement? You integrate it. So we're going to have to integrate the velocity function between 0 and pi, and that would give us our displacement function. So we want the change in displacement over the change in time. So it's going to be the change in displacement over change in time. So we need, in order to figure out our displacement, we need to find the displacement function. So we have to integrate velocity. So let's integrate velocity. So 2 plus cosine t, and we're going to integrate that between 0 and t, and that'll be our change in displacement. So the antiderivative of 2 is 2t, and the antiderivative of cosine is sine. So this is going to be 2t plus sine t between 0 and pi. So this will be 2 pi plus the sine at pi is 0, then minus 2 times 0 is 0 plus the sine at 0 is 0. So that's just going to be 2 pi. So the change in displacement, is going to be 2 pi, and then over the change in time is pi. So the average velocity during that time interval is going to be 2. So again, units are going to be helpful on these problems. So if you want to find average velocity, the units on velocity are distance over time. So you need the change in displacement over the change in time for average velocity. All right. So that's average rate of change. How do you find the average value of a function? Well, to find the average value of a function, what you do is you integrate that function over the time interval. So you integrate from a to b, and then you divide by the change in time. So you integrate the function, and then you divide by the change in time. And another way of writing that, which is very common in textbooks, is you take that b over a, or sorry, the b minus a, and bring it to the outside. So they would write it as 1 over b minus a, then times the integral from a to b, f of x dx. So again, if you want to find the average value of a function, you integrate the function, and then you divide by the change in time. So if we want to find the average value of the function, f of x equals 4 minus x squared on the interval 0 to 3, let's do it. So we're going to integrate from 0 to 4, f of x, so 4 minus x squared dx, and then you divide by the change in time, 4 minus 0. So if I integrate this, I get 4x minus x cubed over 3, and then I want to evaluate that between 0 and 4, and then divide by 4. So this is going to be 16 minus 64 over 3, and then minus 0, all over 4. And so this is going to be 4 minus 16 thirds, which would be negative 4 thirds, I believe. So the average value of that function between 0 and 3 is going to be negative 4 thirds, which doesn't seem right. So let's do that. So we're going to integrate that function between 0. Oh, because I was doing 0 and 4, and it was 0 and 3. So let's try that again. So we're going to go between 0 and 3. 0 and 3. And so let's reevaluate those. And so this would be 12 minus 20, so 12 minus 9, and then minus 0, minus 0. So this is going to be positive 3/4. That makes more sense. So the average value of that function between 0 and 3 is 3/4. Now it wants to know, does that function actually take on that value? So we want to know, does f of x, which equals 4 minus x squared, actually take on 3/4 as a value? So does that function ever equal 3/4 as a value? Well, let's solve for x squared. So we're going to subtract 4 from both sides. So we're going to do 3/4 minus 4. And 3/4 minus 4, we would have negative x squared equals negative 13/4. And so x squared equals 13/4, square root, and x is going to equal plus or minus the square root of 13 over 2. And if we just want it on the interval 0 to 3, the x value that's on 0 to 3 would be the square root of 13 over 2. And so yes, that function actually takes on that average value of 3/4 on the interval. It would take it on at the square root of 3 over 2. That idea is actually going to be the mean value theorem for integrals. All right, let's look at another problem. A glass of lemonade with a temperature of 40 degrees Fahrenheit is left to sit in a room whose temperature is a constant of 70 degrees Fahrenheit. Using the principle of physics called Newton's law of cooling, one can show that if the temperature of the lemonade reaches 52 degrees Fahrenheit in 1 hour, then the temperature of the lemonade as a function of the elapsed time is modeled by the equation temperature equals 70 minus 30 times e to the negative 0.5 t, where t is in degrees Fahrenheit, capital T is in degrees Fahrenheit, and little t is in hours. The graph of this equation confirms our everyday experience that the temperature of the lemonade gradually approaches the temperature of the room. Find the average value of the temperature over the first 5 hours. So average temperature would be like your average value. So to find average value, remember you integrate the function over the time interval, and then you divide by the time interval. So we are going to integrate 70 minus 30e to the negative 0.5t. Between the first 5 hours would be 0 to 5, and then we're going to divide by 5 minus 0. And I'm going to actually just, instead of doing this by hand, we're going to let Desmos do it. So we're going to go between 0 and 5, and we're going to integrate 70 minus 30, and then e raised to the negative 0.5, oops, negative 0.5x and then dx. And so this is going to be 294.925 and then divided by 5. So we're going to divide that whole thing by 5. And you get the average temperature would be 58.985 degrees Fahrenheit. So that's the average temperature of the lemonade during the first 5 hours. All right, so now going back to our concept of derivatives, the mean value theorem for derivatives. So mean, again, means average. So the average of the value of the derivative says that as long as your function is continuous and differentiable. So if you have a function and we are continuous, so you're continuous on the interval, so you're continuous between a and b, so there's no holes, jumps, or asymptotes between a and b, and you're differentiable between those endpoints, so you're differentiable between a and b. You don't have to be differentiable at the endpoints, but as long as you're differentiable in between the endpoints, so there's no corners, there's no cusps, then the average rate of change, so the average rate of change, which again is what we just talked about, f at b minus f at a minus b minus a over b minus a, is going to equal the instantaneous rate of change somewhere between a and b. And the instantaneous rate of change is the actual derivative. What does that mean in terms of like a real world application? What that means is, for example, you're driving in your car, and let's say you go on a road trip and you averaged 50 miles per hour on your road trip. Well, that means that at some point on your road trip, since you averaged 50 miles per hour, at least one point on your road trip, you were traveling exactly 50 miles per hour. You didn't just skip over 50 miles per hour. So if you averaged 50 miles per hour while driving, then at some point while driving, you were traveling exactly on the dot nose 50 miles per hour. And that's all the mean value theorem for derivatives says. That if you have a function and it's continuous and differentiable, then the average rate of change over that value, and remember, average rate of change is the slope of the secant line. So if I were to connect those 2 points, you have this pink line right here. And so that's my secant line. So that's my secant line. What the mean value theorem says is that the slope of that secant line is the average rate of change. So the slope of the secant line is going to be your average rate of change. Somewhere on that graph, you have a tangent line with the exact same slope. So probably about right there. If I were to draw on a tangent line to the graph right there, that would be the tangent line. And the slope of that would be the derivative. And we'll just call that point C. And notice those two lines are parallel, which means their slopes would be the same. So the slope of the tangent line is going to equal the slope of the secant line somewhere on the picture, as long as the graph is continuous and differentiable. And that's what the mean value theorem for a derivative says. That if the function's continuous and it's differentiable, then you can say that the average rate of change, which you find with f at b minus f at a over b minus a, is going to equal the derivative at some location between a and b. So using the mean value theorem. So let's show that somewhere on this parabola, negative x squared plus 8x minus 17, the average rate of change is going to equal the instantaneous rate of change somewhere between 3 and 6. So again, we're trying to prove that f at b minus f at a over b minus a is going to equal f prime at c, where c is somewhere in between a and b. So let's just do this. So this is going to be f at 6 minus f at 3 over 6 minus 3. And we want to make that equal to the derivative. Well, the derivative of this function, remember that's just f prime at x, is going to be negative 2x plus 8. So we want to show that negative 2x plus 8 is going to equal the average value somewhere between 3 and 6. So f at 6 is going to be negative 36 plus 48 minus 17. Then minus f at 3 is going to be negative 9 plus 24 minus 17. And then all over 6 minus 3 is 3. So we're going to get negative 5 minus negative 2, and then all over 3. So that's going to be negative 1. So we want to show that negative 1 is going to be equal to the derivative, which is negative 2x plus 8. And so if I solve this, negative 1 equals negative 2x plus 8. So subtract the 8, and we get negative 9 equals 2x, and then divide by negative 2, and I get 9 over 2 equals x, or x is going to equal 4.5. So at 4.5, which is exactly, or which is in between 3 and 6, we know that the derivative of f at 4.5 is going to equal the average value, which is negative 1. So if I took 4.5 and if I plugged it into the derivative, so 2 times 4.5 plus 8, so negative 2 times 4.5 plus 8, I get negative 1. So the instantaneous rate of change, which is the derivative, is going to equal the average value, the f at b minus f at a over b minus a, at x equals 4.5, which is on the interval 3 to 6. And so that's the mean value theorem. The instantaneous rate of change will equal the average rate of change somewhere on that interval. So let's do another example. Find the values for which the mean value theorem is satisfied. So we have y equals x to the third minus 9x squared plus 24x minus 18. And I want to show that somewhere between 2 and 4, the average rate of change will equal the instantaneous rate of change. So f at b minus f at a over b minus a is going to equal f prime at c somewhere between 2 and 4. All right, so let's plug in 2. So it would be f at 2, or sorry, plug in 4 first. It'd be f at 4 minus f at 2 over 4 minus 2. And we want to show that that's equal to the derivative. And the derivative is 3x squared minus 18x plus 24. So f at 4 is going to be 64 minus 9 times 16 plus 24 times 4 minus 18. Then minus at 2 would be 18 minus 36 plus 48 minus 18, and then all over 2. So let's use Desmos so we don't make any little mistakes. And we would have 64 minus 9 times 16 plus 24 times 4 minus 18. So I have negative 2, then minus 8 minus 36 plus 48 minus 18 minus negative 2 over 2. So my average rate of change is going to be negative 2. And we want that to equal the instantaneous rate of change, which is the derivative. So 3x squared minus 18x plus 24. And now we need to solve this. So I'm going to bring the 2 over. So I have 0 equals 3x squared minus 18x plus 26. And so we want to know when that's equal to 0. So again, you could try and factor and solve, or we could graph it. We want to know when 3x squared minus 18x plus 26 is equal to 0. Well, it's equal to 0 when x is equal to, we would have had to use the quadratic formula, x equals 2.423, or x equals 3.577. And notice both of those are on the interval 2 to 4, so there's 2 places on that graph where the instantaneous rate of change will equal the average rate of change. And that is the mean value theorem. There's another theorem that's kind of like the mean value theorem, and it's called Rolle's theorem, but it's a little bit more specific. So Rolle's theorem says that if you have a function that's continuous and differentiable, so between a and b, it's continuous on a and b, so it's continuous between a and b, it's differentiable, so there's no cusps or corners on the interval a to b. And there's one more stipulation for Rolle's theorem. Where you start and where you end is the same height. So f at a is equal to f at b. So notice f at a and f at b are the same height. So this time when you draw in the secant line, what's the slope of the secant line? Well, the slope's going to be 0. So this is saying that, based on the mean value theorem, the f at b minus f at a over b minus a is going to equal f prime at c somewhere on the graph, but this time the slope is going to be 0. So the Rolle's theorem says that if a function is continuous and it's differentiable, and that you started and ended at the same height, so f at a is equal to f at b, then somewhere between a and b, the instantaneous rate of change, or the slope of the tangent line, would be 0. That's Rolle's theorem. So using Rolle's theorem, so we want to show that f at b minus f at a over b minus a is going to equal f prime at c somewhere on the graph, but this time it should equal 0 if Rolle's theorem works. So we're going to take f at negative 1 minus f at negative 3 over negative 1 minus negative 3, and then the equals the derivative, which is 2x plus 4. Well, f at negative 1 would be 1 minus 4 plus 5. Then minus f at negative 3 would be 9 minus 12 plus 5. And then all over negative 1 minus negative 3 would be 2. Well, we would get 6 minus 4 is 2. Then minus 9 minus negative 12 is negative 3 plus 5 is 2 over 2. So this is going to equal 0, which is what we wanted. So we want to show that the derivative is equal to 0 at some point. So 0 equals 2x plus 4. Subtract the 4 and divide by the 2, and you get x is equal to negative 2. So where does the derivative equal 0 on that interval? Well, f prime of x is equal to 0 when x is equal to negative 2. So Rolle's theorem works. So that's an example of Rolle's theorem. And again, the mean value theorem for derivatives and Rolle's theorem both deal with the derivative of a function. The mean value theorem for integrals is going to deal with integrals. So what the mean value theorem for integrals says is that the average value, and we just talked about how to find average value, so the average value of a function is going to equal the instantaneous value of the function somewhere on the interval, as long as your function is continuous. So as long as the function is continuous, the average value, and remember how we find average value is you integrate the function between a and b, and then you divide by the function. And then the instantaneous value is just going to be the function value at c. So for the mean value theorem for integrals, what you're saying is that the average value of the function will equal the instant value of the function somewhere between a and b. So let's use the mean value theorem for integrals. So find the value or values of c guaranteed by the mean value theorem for integrals for the function over the given integral. So we want to show if I integrate between a and b, f of x dx over b minus a, it's going to equal the actual function value somewhere between a and b. So we are going to integrate between 0 and 3, x cubed dx, all over 3 minus 0, and we want to show that that's actually equal to the function somewhere. Well, the function in this case is x cubed. So I want to show that the function is going to equal the average value somewhere between 0 and 3. So if I integrate, I get x to the 4th over 4, and we want to integrate between 0 and 3, and then divide by 3. So that would be 64 over 4 divided by 3, so that would be 64 over 12 equals x cubed. And so to solve for this, we would take the cube root of both sides. And so x is going to equal the cube root of 64 twelfths. And we want to show that that's somewhere between 0 and 3. So if I take the cube root of 64 twelfths, so 64 divided by 12, and then take the cube root of that, so take it to the 1/3 power, and you get 1.747. And that is on the interval 0 to 3. So where does the average value of the function equal the instantaneous value of the function? It will at x equals 1.747. All right, let's look at another one. We have 2 secant squared x. We want to know when the average value would equal the instantaneous value between negative pi over 4 and pi over 4. So we would integrate between negative pi over 4 and pi over 4. I'm going to pull the 2 out, and then secant squared x dx, then all over the change in the value, so pi over 4 minus negative pi over 4. And we want that to equal the function secant squared x, 2 secant squared x. So if I integrate secant squared, I get tangent. So I get 2 tangent x between negative pi over 4 and pi over 4. And then divided by pi over 4 minus negative pi over 4 would be 2 pi over 4, which would be pi over 2. And that's going to equal 2 secant squared x. The tangent at pi over 4 is 1, so this is 2 times 1. Then minus the tangent at negative pi over 4 is negative 1, so 2 times negative 1. That's going to equal 2 secant squared x. And so this is going to be 2 plus 2, so we want 4 to equal 2 secant squared x. Divide by 2, divide by 2. And so I want secant squared x to equal 2. So we're going to take the square root of that. So we get plus and minus the square root of 2 equals secant x. And where does secant equal the square root of 2? Well, secant equals the square root of 2 at pi over 4, and it equals negative square root of 2 at 3 pi over 4. So all of the pi over 4 works, but we want between negative pi over 4 and positive pi over 4, so it's going to be at pi over 4 and negative pi over 4 is where the average of a value would equal the instantaneous value of that function. All right. Now we're just going to do a couple review problems. So go ahead and pause the video and see if you can review how to find these different definite integrals. So integrate sine x between 0 and pi. Integrate secant squared dx, or secant squared x between 0 and pi over 4. Integrate 1 over x between 1 and e, and integrate 3x squared between negative 1 and 2. So go ahead and pause the video and try those, and then you can check your work against the finished notes from class today. Your homework is your worksheet over